you know, seeing the BCA method and then also seeing the traditional method probably was like just too much overload. So I think unless somebody is adamantly opposed to it, I think we should just kind of stick with the BCA method for limiting reactant problems. And that doesn't mean that you can't do traditional for literally everything else, okay? And I'll tell you right now, there's probably only going to be 1 or 2 limiting reactant problems on your test, all right? So it's not going to be like you have to do 85 of these problems in BCA and you hate it and blah, 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 all right? So I think it's probably appropriate for us to kind of stick with our BCA for limiting reactant. All right, so I do want you to submit what you could have worked, like what you did yesterday on yesterday's assignment. It's okay if something is totally wrong or whatever. We're going to go through number 4 here together, and then I'll do at least one other limiting reactant problem with you as well. Your assignment today is, I think it's 8 problems, but only like 2 or 3 of them are limiting reactant, and it's not due until Tuesday because Monday is an asynchronous day. And my assignment for you on Monday is to complete your work from today and submit it by Tuesday morning, okay? So keep that in mind. All right, here we go. Sodium hydroxide reacts with sulfuric acid. Okay, so let's start by writing this reaction out. Sodium hydroxide, sulfuric acid, to give us the formula there. Water and sodium sulfate are my products. Here's the water. And sodium, positive 1, sulfate, minus 2, so Na2SO4. All right, let's see. 2, 1, 2, 1, I think, is how we balance that out. All right, so it tells us that we are starting with 15.5 grams of the sodium hydroxide and 46.7 grams of the sulfuric acid. And they want the mass of sodium sulfate, okay? So what that means to me is they don't care about water, which means I don't care about water, which means we can do a little squiggly in the water column, okay? I don't need you to do the extra work at this point in time. You did the extra work at the beginning of the unit to get more practice, okay? Now that we're becoming, a little bit more confident with these problems, we are going to kind of eliminate the need to do like all this extra practice. All right, first things first, I need to convert my grams into moles, all right? Here's what I like to do personally, all right? I like to calculate my molar masses first, and then I like to do all my other conversions because molar masses slow me down, right? They slow everybody down, unless you're like memorizing the periodic table. So I'm going to go ahead and calculate the molar mass of sodium hydroxide. I'm going to calculate the molar mass of H2SO4. And I'm also going to calculate the molar mass of the Na2SO4 because, I can say, well, how do you know I need that? Well, they're telling me that they want the mass of the sodium sulfate. So that means in my BCA table, I'm going to get moles, and then I'm going to have to convert it into grams, and I know I'm going to need molar mass, okay? If you don't want to do it like this, in this order, it doesn't bother me. I just want to share with you how I solve these problems. All right, so let's calculate here. 22.989770 is sodium's mass, plus oxygen is 15.9994, plus hydrogen, 1.00794. All right, and I get a total molar mass of something. 40.00 grams per mole. Okay, I'm going to go ahead and do the same for my H2SO4. 2 times the mass of hydrogen plus sulfate 32.066 plus 4 times the mass of oxygen. Bless you. All right. H2SO4 molar mass comes out to be 98.08 grams per mole. All right. Last, I'm going to do that molar mass for my Na2SO4. 2 times the mass of sodium, 22.989770, plus sulfur is 32.066, plus 4 times the mass of oxygen, 2.9994. All right, and that comes out to be 142.04. All right, let me zoom out so you guys can see all that, in case you missed something there. All right, everybody with me so far? Just a bunch of molar mass calculations, all right? Again, I like to get those out of the way first because then I am basically just converting, okay? So let's convert. We have 15.5 grams of sodium hydroxide. So let's go ahead and put that into moles. So 15.5 grams of NaOH over 1. I just calculated my molar mass there of 40.00. So I can basically just plug that in. The denominator on the top goes 1 mole. And then we end up with 3 sig figs here, 0.388 moles of NaOH. All right, simple gram to mole calculation. This is going to go in my B part under the NaOH. 0.388. All right, now let's take our 46.7 grams of sulfuric acid. Which is H2SO4. 1 mole of H2SO4 on the top. And our molar mass for that we found to be 98.08. So plug that into the bottom. All right, again, looking for 3 sig figs here, I end up with 0.476 moles of H2SO4. All right, any questions so far? So far, we really haven't done anything new in stoichiometry, right? We've just calculated molar masses, and then we've just converted from grams to mole. Okay, nothing like too crazy new. All right, so let's put that value into our table up here, 0.476. All right, can anybody tell me, we can put our 0 in for Na2SO4 as well while we're up there. I always forget to do that. Can anybody tell me what my next step is? You don't have to tell me the numbers, but like, what do I need to do here because it's limiting reactant? Dalen, what do you think? Good. Good. So I have to go to moles from, I'm going to start with these mole amounts. I'm going to go to moles. Basically, what I'm going to do is try to go from my moles of NaOH, and I'm going to see how many moles of H2SO4 those moles of NaOH would require if I were to use them all up, okay? Remember, our definition of limiting reactant is basically the thing that we're going to use all of it, right? The grammar there is terrible. Please don't tell your English teachers. All right? Whatever we're going to use all of is our limiting reactant. So we're going to go from 0.388 moles of NaOH, and we're going to see how many moles of H2SO4 that would require. And then I'm going to ask you, do we have enough? All right? This is a straightforward mole-to-mole ratio calculation. So I need my coefficients for my balanced chemical equation. There's a 2 in front of my NaOH, and there's a 1 in front of the H2SO4. So 0.388 divided by 2 gets me 0.194 moles of H2SO4. Now, here's the question, right? And like every time you do this problem, you should be asking yourself this question. Do I have at least that amount? I do, yes. In fact, I have a lot more than that, right? I have 0.476 moles of it. So 0.194 is less than 0.476. You can all agree with me on that, okay? What this tells me is that this NaOH is the limiting reactant, and that means I am going to use up all of it. All right, so now I can come up to my table and subtract my 0.194. I can subtract all of my NaOH. All right, now the limiting reactant, which is the NaOH, is going to dictate the rest of the table. It's going to dictate the rest of the problem, okay? So what that tells me is I'm going to use that 0.388 moles of NaOH to figure out how many moles of my sodium sulfate I'm going to produce, okay? So again, I'm going to do another mole-to-mole calculation down here. So 0.388 moles NaOH, limiting reactant. How many moles of Na2SO4 will it produce? We can do that with a mole over mole ratio here. Na2SO4 has a coefficient of 1, NaOH has a coefficient of 2. So we end up with 0.194 again moles of Na2SO4. Okay? Now we have to put that into our table. And then we're almost there, guys. I'm going to do a plus on that because we know it's a product, we're producing it. And now we can go ahead and fill out our after row. So we end up with 0 moles of NaOH left, which is right, because that's our limiting reactant. We're going to use it all up. 0.476 minus 0.194 leaves us with 0.282 moles of our H2SO4. And then we end up producing 0.194 moles of our Na2SO4. All right, now the problem does ask us for the mass of sodium sulfate. I have my moles right here, right? So now I just need to take my moles of that and convert it to grams. And guess what? We already calculated that molar mass, all right? So we're ready to go. We can just start setting this up. So 0.194 moles of Na2SO4. All right, and then we're going to have the molar mass of the Na2SO4, which is the 142.04 we calculated. Grams Na2SO4 on the top, 1 mole Na2SO4 on the bottom. Still looking for 3 sig figs here, friends. We end up producing 27.6 grams of Na2SO4. All right, and that's the answer to the question they asked us. They asked us for the mass of sodium sulfate produced here. All right. What questions do you have?
So like I understand where like I understand like the values and like the limited reactant, but I don't understand where they go in the BCA table.
Okay, so what values aren't you sure where they go? Are you talking about like the 0.388 or the 0.476, or are you talking about the 0.194?
Kind of just all of them.
Okay, all right, so for the first two that I calculated here, those are the beginning amounts because we were given the 15.5 grams and the 46.7 grams of the H2SO4. And if you look at the problem, and I'm not going to lie to you, I can't really give you a problem that's really different than like all of the practice that we've done. You're always going to get the starting amounts of both of your reactants for a limiting reactant problem, okay? So those values are always going to go in the before because that's what we're starting the reaction with, okay? Now, when you calculate and figure out what the limiting reactant is, you're essentially calculating the change value for the other reactant, for the excess reactant, okay? Because think back to when we first learned BCA tables, this process that we're doing right here was the same way that we just solved for the change row in our normal BCA tables, okay? And then last but not least, this calculation here, where we go from the moles of the limiting reactant to moles of the product, it's the same idea as when we started our BCA tables. We're just trying to figure out how much of that product I will produce based on the mole ratios there, okay? So let me simplify that into like a more concise statement since that was a lot. Anything that you calculate using a mole ratio, that's going to go in the change row in the BCA table. Does that help?
Yeah.
Okay. What other questions do you have, guys? Nothing right off the bat? All right, shall we take a look at today's assignment? We're going to do another limiting reactant problem, so don't feel like we're just moving on. All right, so I want to first take a look here. I believe we have 9 problems. Is that right? Yes, 9 problems. All right. Now, let's circle the ones that are going to be limiting reactant. Okay. Number 5 is limiting reactant. Number 7, 8, and 9 are limiting reactant. Okay? All right, let me pick a good one. I think we're going to do 5 because 5 actually asks us to calculate the percent yield after we find the limiting reactant, which you might be like, oh my gosh, but it's really not that deep. So we'll probably go ahead and do that one. And then if you would like, we could also do number 8 or number 9 because those questions ask us for the mass of the excess reactant that remains, which we didn't do in number 4 that we just practiced. But basically what that requires is you would take your moles of your excess reactant that you have at the end and just convert that into grams. Okay? So let's start with number 5, and then we'll see how you're feeling. If you guys are like feeling like you're ready to do these on your own, then I don't have to do more of them with you. Okay? Just you guys just have to let me know how you're feeling. Other than happy that it's Friday. All right. Let me get my work just so I have the molar masses for us. Yeah, number 5 is a little annoying. All right, let's do it. It says in the copper silver nitrate lab, we actually do this lab if COVID was not occurring. Copper, metal, and silver nitrate solution react to produce silver metal and copper 2 nitrate in solution. Okay, so let's write out our reaction. You know the drill. So we've got copper reacting with the silver nitrate. Silver is +1, nitrate is -1, so we end up with AgNO3. And that's a solution, so it's going to be an AQ on there. And then it produces silver metal. Oops, I should have had a solid on copper, guys. I'm sorry. Back and fix that. There we go. All right, so silver metal, which is going to be Ag solid plus copper 2 nitrate. So it's going to be CuNO3 2. Okay, copper is +2, nitrate is -1, so I need 2 of the nitrates to balance that out. And that also says solution, so that guy is going to be aqueous as well. All right, let's balance this guy. So I'm thinking a 2 here, a 2 here, 1 and a 1. So 1, 2, 2, 1. All right, the next thing that I want to do here, guys, is just draw my BCA. I got to squeeze it in on the side here. All right, now let's look at what they give us. They give us a mass of copper, the 2.93 grams. They give us the silver nitrate solution, 1.41 grams of silver nitrate. Now, I already spoiled the surprise and told you it was a limiting reactant problem. But if I hadn't spoiled the surprise, you could recognize this as a limiting reactant problem because you're given amounts of 2 reactants. If you're only given the amount of 1 reactant, you can't do a limiting reactant problem. Okay? All right, so it says he actually obtained 0.87 grams of silver metal. Calculate the percent yield of silver. So what that tells me is that I'm going to need grams of silver. Okay? So that tells me this copper 2 nitrate over here gets a nice little squiggle in his column. I don't have to worry about it.
Wait, why don't you worry about that?
Because they're asking me for the percent yield of silver, the first product. And so I'm not going to need to calculate anything with the copper 2 nitrate. So at this point in time, we're allowed to just give him the squiggle. All right. Now let me think. I'm going to need the molar mass of copper, which is easy because it's just an element. I'm going to need the molar mass of AgNO3, so I need to calculate that. And then I'm going to need the molar mass of Ag, but that's simple because it's just an element. So really, our molar mass calculations can be a little quicker. We really just need the molar mass of AgNO3. All right, because the other molar masses I can just pull right off my periodic table. All right, so silver is 107.8682. Plus nitrogen is 14.00674. Plus 3 times. Crap, I ran out of space. I'm going to come down here and write the oxygen mass, guys. Sorry about that. And 4. All right, so the silver nitrate mass comes out to be 169.87 grams per mole. All right, so our first step is going to be convert your grams of your reactants into moles so we can put them into the BCA table. All right, so let's start with our copper. We're given 2.93 grams of copper. Converting that into moles, I'm going to have 1 mole of copper on the top. I'm going to have copper's molar mass in the denominator, 63.546 grams Cu. Keep those 3 sig figs there. This is going to be an annoying number just because it's so small, but it's 0.0461 moles of Cu. All All right, so that is my before. That's what I'm starting the reaction with for copper. So let's go ahead back up here and put that into our BCA table under our copper. Now they give us the 1.41 grams of silver nitrate, so that's our next calculation. Okay, we calculated that molar mass 169.87. Three sig figs again. Another slightly annoying number, 0.00830. I have the 830 there for the three sig figs because those first two zeros are not significant. Yeah.
Why did we round like the first like mass of like the green one to 3 decimal and not 2?
Oh, the molar mass?
Yeah.
That's my bad. We can put that as 0.55. Sorry, that's my mistake. Good question. All right, so this 0.00830 is our B before amount for our silver nitrate. So let's go back up here and put that into our table. 0.00830. And then for our product of silver, we still end up starting with 0 moles. All right, so let's see which one of my reactants is limiting. All right, I'm going to start with the 0.0461 moles of copper, and I'm going to convert that to moles of silver nitrate to see if I have enough of it. So this is going to be my mole-to-mole calculation. Okay, we have 2 moles of AgNO3. That's my coefficient. And 1 mole of copper. Okay, that comes out to be 0.0922 moles of AgNO3. Now stop and ask yourself the question, do I have at least this amount? Do I? No, I have 0.00830 moles of silver nitrate. That's a heck of a lot less than this 0.09. All right, so my answer to that question is no. So that means copper cannot be my limiting reactant. Okay, so now I need to try the opposite, right? I need to go from my 0.00830 moles of AgNO3 and see if I have enough copper to react with that. It's going to be 1 mole of copper on the top, 2 moles of AgNO3 on the bottom. That comes out to be 0.00415 moles copper, right? I'm going to ask you the same question. Do I have at least this amount of my copper? Decimals are hard. The answer is yes, because I have 0.0461. Okay, so 0.00415, that's way less than 0.0461. Okay, so yes, so that means AgNO3 is my limiting reactant, and that means copper is what we call our excess reactant, or ER. Okay? So now, this amount that you just calculated, this is going to be the change for my copper. All right, so let's come back up to the table here and put that in. Right? Because AgNO3 is my limiting reactant, I'm going to use all of it up. Now, I'm going to teach you a little bit of a trick. Do you see how the coefficient in front of silver, the product, is the same as the coefficient in front of the silver nitrate? They're both 2's. Does anybody know what that means in terms of the amount for silver? Anybody? It's the same. Now, if you're uncomfortable with that, that's fine. You can calculate it out. All right, there's no shame in either of those games. A lot of people, you've probably started to recognize kind of, those patterns or those things. Okay? All right, so now let's do our after. A bit of subtraction to do here. 0.046 minus 0.00415 leaves me with 0.0420. This leaves me with 0, and this leaves me with the same amount. All right, now let's take a step back. We did our BCA table, but what is the problem actually asking us for? What's the percent yield? Okay. Can I use moles in a percent yield calculation? No, I have to go to grams. Okay. So I'm going to take our 0.0083, convert him into grams, which is why we calculated. Oh, we didn't even calculate because it's silver. We don't even calculate that molar mass. All right. Let's go ahead and set that up. Moles of silver. We're going to go to grams of silver. My friends, this is going to be our theoretical yield. Do we remember that fun term? Yep. All right. All right. I end up with 0.895, still 3 city figs, grams of Ag. This is theoretical yield. All right, remember how we solve for a percent yield? What do we do? Good. Actual over theoretical times 100, beautiful. They still have to give us the actual. They can't trick you there, okay? They give us 0.87 grams, 0.895. Now this one's a little weird because the 0.87 has 2 sig figs. The 0.895 has 3, so technically I should have 2 sig figs in my final answer. All right. I get 97% yield of silver. All right, how do we feel? We feel like considerably better than yesterday, or only
I
slightly?
have a question.
Yes, ma'am.
So, I think I understand, but I just want to make sure. So, because the AgNO3 is the limited reactant, you use all of it. That's why it's the 0.00830. And then since copper is the excess. That's why you use the calculation of the 0.00415.
Yes, ma'am, that's perfect. Absolutely perfect. All right, friends, what would we like to do? We have about 17 minutes left. Do you want me to stop? Do you want me to do another problem? It's totally your call. What? Archie, I'm sorry, I can't hear you. Yes. For the one we just solved? Yeah, percent yield of silver. All right, what do you guys want? Another problem or for me to hush? I won't be offended either way. Yeah, I'm doing it. Did you need the final answer there, Archie? You got it? Okay. All right, so let me pick a good one here out of the limiting reactants. Let's go ahead and do number 8 because number 8 requires us to get the mass of the excess reactant. So that's a little bit different than what we just did. All right. All right, let's see what we're working with here, number 8. So they have zinc sulfide and oxygen gas react to form zinc oxide and sulfur dioxide. Okay, let's write our reaction out first. So zinc is +2, sulfide is a -2, so we're going to have ZnS, plus oxygen gas is O2G, forms zinc oxide, zinc is +2, oxygen is -2, so ZnO, and sulfur dioxide is SO2. All right, let's balance this puppy. All right, I think it's 2322. All right, so let's read it. It says, determine the amount of ZnO that should be produced in a reaction with 46.5 grams of ZnS and 13.3 grams of oxygen. What is the mass of the excess reactant? Okay, so they do not mention anything required for my SO2, so I can squiggle him out. I'm going to go ahead and calculate the molar mass of ZnS, O2, and ZnO. So I'm going to need all of those gram amounts eventually. All right, so ZnS is our first one. Zinc is 65.39 plus 32.06. And that comes out to be 97.46 grams per mole. Next is the molar mass of O2. That's just 15.9994 times 2. Gives us 32.00. And then the zinc oxide, 65.39 plus 15.9994. And that gives us 81.39. Oops. What do you do? Besides hammer something. They're just hammering.
Is that a clip?
I think that's the wood shop. Yeah. What?
Isn't that a pumpkin?
Gangrene?
Yeah,
They're the, the horticulture club.
I don't get it. It's so pretty down there, and they don't let anybody in there.
I know.
Like, they should teach a class down there or something.
The door's unlocked. I take my third block down there during study hall. Because we have so much extra time. The door's unlocked. You can technically go out there. Well, I don't know. Maybe you need a teacher. I don't know. All right, let's do it. So we need to convert our 46.5 grams of ZNS to moles. All right, 97.46. All right, I end up with 3 sig figs here, 0.477. Much better number than the last BCA table. All right, that value is our before value for ZNS. So let's go up to our BCA table and put that in there. All right, and then we'll go ahead and calculate our moles of O2. So we're starting with 13.3 grams of it. 1 mole of O2, 32.00 grams of it. And 3 sig figs again, we end up with 0.416 moles of O2. All right, so that's our V for oxygen. So let's put that in there. And we begin with 0 moles of zinc oxide. All right, let's go ahead and try to figure out what our limiting reactant is. So I'm going to start with the 0.477 moles of ZNS. And I'm going to go to moles of O2. So we get 3 moles of O2 on the top, 2 moles of ZNS on the bottom. Get 0.716 moles of O2. Here's my question. Do I have at least this amount? Do I have it? No, I don't. I only have 0.416. So this is not going to work. No. All right. So now we need to try starting with our 0.416 moles of oxygen and see how much ZNS that would require. So we'll have our 2 moles of ZNS on the top, 3 moles of O2 on the bottom. That comes out to be 0.277 moles of ZNS. There's my question. Do I have at least this amount? Yes. So yes, we do. So that means O2 is my limiting reactant, and then ZNS is my excess reactant, or ER. All right, so where does that 0.277 moles of ZNS go in my BCA table? 0.277, and it's a minus. Okay? If O2 is my limiting reactant, how much of it do I use up? All of it. Okay? Now, you might be looking at the coefficients, right? The last time we kind of had the same coefficients. This time we don't have the same coefficients. But what do we recognize about the coefficient of ZNS and ZNO? They're the same, right? So I bet you we're going to end up with 0.277 moles of RCNO. But let's prove it. Okay, and we do. We end up with 0.277 moles of our product. Yeah, absolutely. And I'm going to put this 0.277 in there too. I'm going to go here. All right, now we can figure this out, right? Subtraction, little addition maybe. We end up with 0.200 moles of our ZNS left over. We end up with 0 moles of our limiting reactant left over. And then we end up with 0.277 moles of our product. Now, remember, this question was different from our last one because it wants the amount of ZNO, so it wants the grams of our zinc oxide, okay? But it also wants the mass of the excess reactant that remains. All right, so what we're going to do is we're going to take our moles of our ZNS and convert that into grams to answer that one question, okay? So even though this problem is a little bit different, guys, it's not more complicated, right? It's just another mole to gram calculation, okay? We actually already calculated the molar mass of ZNS earlier because we needed that to begin our problem, okay? So I'm going to calculate that out. 3 sig figs still. That comes out to be 19.5 grams of ZNS. That is how much remains, or how much is left over. All right, do you understand that extra step there? It's just another moles to grams, guys. All right, to finish off the problem, let's calculate our grams of ZNO that was produced because they did ask for that. So we're going to take our 0.277 moles of zinc oxide. Yes. Again, we already have our molar mass for zinc oxide, right? Because we calculated all of those at the beginning. All right, 3 sig figs yet again. We end up with 22.5 grams of zinc oxide. And I'll label this as well. This is how much is produced. Okay. How do we feel? Better? It's a lot. Yeah, it is a lot. Yeah. All right. So I'm going to put this meetup on Canvas. Okay. So if you need to, when you're going through the problems this weekend, if you need to hear the explanation again, it's going to be there. Okay. You guys only have 2 more limiting reactive problems to do, 7 and 9. The other problems are just like regular conversions, so you're going to be able to use your traditional method with them. Okay? Virtual people, you're free to go. Have a wonderful rest of your day and a wonderful weekend, okay? I'll see you guys all on Tuesday, virtual day on Monday, okay?
Thank you.
Are you ready?